Professor Kamakodi and his team. These are the topics today I would like to cover. That is small introduction about INC system for reactor applications, need for IP core based processor, then why SHAKTI processor is selected and its features, roadmap for SHAKTI processor based systems, then our achievements. INC system. INC systems plays a vital role in reactors. It monitors the plant parameters 24/7 and control the reactor operations. It also protect the plant as well as the plant personnel. In modern nuclear power plants, computer-based systems are extensively used for INC. INC systems are indigenously designed, developed as per the AERB safety guidelines. It has to be qualified for EMI, EMC, environmental and seismic qualification. Then we have to verify and validate the system. Then we have to obtain the AERB clearance. INC systems are categorized into safety critical, safety related and non-nuclear safety systems as per the dependability and importance of the system. Safety critical system plays a principal role in achievement of nuclear power plant safety by safe shutdown of the reactor followed by decay heat removal from the core and containment of the radioactivity. Safety related systems plays a complementary role in achievement or maintenance of the nuclear power plant safety. The efficient operation of the safety related system reduces the demand on safety critical system, thus enhancing the availability of the plant. NNS plays an auxiliary or indirect role in the achievement or maintenance of nuclear power plant safety. They can be part of total response to an incident, but not be directly involved in mitigating the physical consequences of the incident. Different architecture is followed for each category. For safety critical system, triple modular redundant architecture is followed by 2/3 voting logic. Sorry.
Hello.
1 second, sorry. Hold. Safety critical system, triple modular redundant architecture is followed by 2/3 voting logic for safety actions. For safety related system, dual redundant system with hot standby configuration is used with switchover logic system. Here, two RTC systems will be there, RTC1 and RTC2. Both systems will be scanning the plant inputs and do the processing and give the output signals and health signal. Depending upon the healthiness of the system, the switchover logic will route the output to the plant. Initially, RTC1 system's output will be routed to the plant. If RTC1 fails, then RTC2 system's output will be routed to the plant. For NNS, single dedicated embedded system is used. This is the distributed architecture adopted in our plant. It is having the 3-tier architecture. Separate dual redundant LAN is provided for each category of the system. These are the INC system design criteria. System should be simple in design, highly available. It should not fail. If at all it fails, it has to fail in the safe mode. We cannot design a system without any failure. There will be a fault. So fault avoidance is achieved by derating of the components and systematic approach. But we cannot completely avoid the fault. So fault tolerance should be provided with redundancy and diversity. System should have single failure criteria. Fault detection and indication will be achieved by online diagnostics. System should be testable, highly available. Surveillance should be provided. There should be independent verification and validation of the system. Computer-based INC system comprises of CPU card, analog input and output cards, digital input and output cards, motion control cards, then input-output backplanes. Fault-tolerant power supply modules are provided for load sharing and fed from diverse feeders. Important functions of computer-based systems are scanning the inputs from the sensor, processing the logics, diagnostics, then generation of output for actuators or final control elements, and sending the processed data for storage and display purpose. Software should be fused in the EEPROM. There should not be any operating system. These are the design and development methodology followed for INC system. It should start from design basis report. Then system requirement specification has to be prepared. Then architectural design has to be done. Then this is the hardware path and this is the software path. Software requirement specification, software design description, and software implementation. Same way, hardware requirement specification, hardware detailed design, then hardware implementation. Then the system integration and test report has to be prepared. Then validation at the site. Then only the system has to be commissioned for operation. Here, what I want to insist is each stage the verification has to be done. This is the typical INC system cabinet. This is a dual cabinet. This is one RTC system and this is another RTC system. This is the switchover logic system. This is the lab setup. So we are having DI and AI simulators are there. Here, the single cabinet, these embedded systems are placed. Need for IP core based processor. Why we need IP core based processor? Obsolescence of electronics is a main problem in the industry. So if you take system life versus component life, nuclear power plants are designed to operate 40 to 50 years. But the electronic components used in INC systems becoming obsolete in 10 to 15 years. If you take the system life, that is date of introduction. If 1991 system is introduced, the expected end of life will be 50 years. If 2020 it is introduced, it will be around 70 years. 2050, then it will be 80 years. The system life will be increased with the time. But if you take the component life, if 2006, some 12 lakhs components will become obsolete. 2007, some 10 lakh. 2008, 14 lakhs. And 2009, some 11 lakhs. Approximately every year, some 10 lakhs components will become obsolete. So if you see this introductory data and purchase time, initial days, these components will be available more time for purchase. But nowadays, it is not available for more time. Maximum 5 years, the components will be available. It will become obsolete. How to mitigate this problem? This is the common situation. At the time of introduction, installation itself, most of the component, that is 70% of the component will become obsolete. Then if after some times, all the components will become obsolete. So how to mitigate this problem? Two mitigative plans are there. One is reactive, that is reacting to the problem after it arises. Proactive, that is preventing the problem before they arise. A proactive approach focuses on eliminating the problems before they have a chance to appear, and a reactive approach is based on responding to the event after they have happened. In reactive type, you have to buy for lifetime, last time buy, aftermarket sources, identification of alternatives or substitute particles. In proactive type, identifying and prioritizing the selected non-obsolete parts that are at risk of obsolescence and identifying resolutions for them before they are discontinued. Then what's the solution for the processor obsolescence? Processor is the heart of any INC systems. So obsolescence of the processor used in INC system creates demands not only on the hardware, but also the software used in the system. So we have to go for HDL, hardware description language based designs with open specification, open tool chain for application development, complete verification framework for open specifications, FPGA or ASIC route we have to take. Then there should be a provision for integration with third-party peripherals. Why we have selected SHAKTI processor and features of SHAKTI processor? In general criteria for processor selection for safety applications are there should not be any bugs listed. It should be available from more than one vendor. It should have proven track record. With this in mind, to overcome the processor obsolescence, open source RISC-V ISA based SHAKTI soft core processor developed by IIT Chennai is considered for computer based systems of fast breeder reactors. SHAKTI processor has open specification, complete verification framework is available, expertise is there. It is one advantage is near to us. This IIT Chennai. Then it has obsolescence free roadmap. It provides backward compatibility. So RISC-V is a free and open instruction set architecture. It is started for academic and research purpose. Anyhow, it is going to rule for next 50 years. Foundation has 7 representatives like BlueSpec, Google, Microsemi, like that. What is mean by instruction set architecture? In before 1960, the program developers will write program for the unique hardware. Once the hardware becomes obsolete or new release comes, the software developed for the hardware cannot be used for the next release. We have to start the software development from the scratch. So, but software development is very much costly. So, in 1960, IBM introduced instruction set architecture and microcode engine. It is a boundary between hardware and software. ISA includes data type supported by the hardware, memory model and register mode, instruction set and IO model. IIT is having 7 types of SHAKTI cores. 7 variants are available. C class for embedded application, I class for server, general purpose computer, M class is developed. For S class for superscalar, H for HPC, P for secure, F is for fault tolerant. We have selected C class embed because it is for embedded system application. SHAKTI C class is an RTL implementation of RISC-V specification. It is available as design written in BlueSpec system Verilog, completely open source under BSD license. It is a license for open source software. 2 tap outs are available, Intel 22 nanometer technology and from SEL 180 nanometer technology. This is the Intel chip and this is the SEL chip. This is the SHAKTI C class micro architecture. The specifications are it supports RISC-V ISA 64-bit processor. It has single and double precision floating point units compliant with IEEE 754. Supports open on-chip debug based debug environment through JTAG. It includes high performance branch predictor with random access stack. Caches, it is having 16 to 64 KB non-blocking pipelined instruction and data caches. Option is L2. It includes operand forwarding scheme for better performance. Boots RISC-V Linux. Compatible with the latest privilege specification, that is version 1.10. This is the commonly used workflow in RISC-V. The implementation in Spike. OS kernel is proxy kernel and Linux are available. System libraries newlib and GLBC. Compilers Glang, LLVM, GCC. Then distribution is open embedded, Gentoo and BC. This is the RISC-V GCC. C program is written and it is compiled through the RISC-V compiler. Then assembly language program is generated and it is fit to the assembler. It generates machine language module. It is linked with the library routine through the linker and executable is generated and it is loaded into the memory. Verification of the C core. Verification of processor is a very difficult job. So IIT is doing this verification of the C class core. Random program generator is generating the valid random program and through the spike and C-class module, state dump is taken and it is compared. If it is matching, it will go for the next program. Otherwise, debug has to be done. This is the roadmap for SHAKTI IP core based processor. We are having 68020 processor based CPU card in PFBR. So initially, first we thought replacing this 68020 processor with a SHAKTI processor through the piggyback board to have the proof of confidence. Then porting the majority of the application into that SHAKTI processor and testing. Then development of a full-fledged CPU card version 1.0 with SHAKTI processor. Then we would like to deploy in the field. Then development of version 2.0 SoC based SHAKTI CPU card with the SHAKTI IP core and peripherals. This is the existing VME bus based CPU card with the 68020 processor and 68882 floating point processor. It has the VIC controller, EEPROM 1 MB, SRAM with ECC 2 MB, E2PROM for configuration 128 KB. It has control logic and VME interface logic, 4 numbers of serial ports and 2 numbers of local area networks. This is the block diagram of the CPU card. Here we want to take the CPU and floating point unit, and this is replaced with the SHAKTI processor. All the other peripherals we want to use the same. This is our proposal. This 68020 and floating point processor are replaced with the SHAKTI IP core. Then wrapper logic is developed. SHAKTI processor based picky board was designed as a snap-in pin-to-pin replacement for existing 68020 CPU baseboard. Piggyback board is designed which act as a snap-in pin-to-pin replacement for 68020 on CPU baseboard without altering the control glue logic, EDAC logic, and VME interface logic. This board consists of Arctic 7 FPGA associated with power, reset, clock level, translation, debug circuitry, and pin grade for connecting the 68020 CPU card. Power, reset, and clock for piggyback board are derived from the CPU baseboard. Power supply sequencing of core and input-output modules of FPGA is done by power. Its associated wrapper logic is being implemented in Arctic 7 family FPGA from Xilinx. JTAG port and serial port are provided on piggyback board for debug purpose. JTAG port is also used for loading FPGA configuration data onboard flash memory of piggyback board. Unidirectional and bidirectional level translators with latch-up protection are provided on piggyback board to enable voltage compatibility across voltage domains of piggyback board and CPU baseboard. To establish software compatibility, the application programs of 68020 CPUs modified. Wrapper logic is established the hardware compatibility with 68020 CPU card. SHAKTI processor is associated with the wrapper logic. Wrapper logic translate the SHAKTI core's read-write cycles to 68020 read-write cycles respectively. It converts 64-bit transaction to 32-bit because our CPU card is 32-bit. Wrapper logic includes interrupt handler also. It is designed by IIT Chennai. This is the CPU card with piggyback board. This is the piggyback board. This CPU card, this processor and floating point processor are removed, and this piggyback board is placed on top of this existing CPU card. The next level is porting the typical INC application software and testing. This is the general flowchart for application software. That is start, then RAM check, memory check, then initialize the peripherals and IO cards, then waiting for the configuration data from the server. If it is received, then it will be continued. Otherwise, it has to wait for the configuration data. Then after getting the configuration data, enable the watchdog timer, load the timer 1 second or 5 seconds, then scan the inputs, processing, then diagnostic logic, then generate the control and interlock outputs, then generate soft outputs. Refreshing the watchdog timer, receive the soft input and send the data If a timer expires, then this loop has to be followed. This is the typical application software flowchart. Then the application software is developed. Then the CPU code is tested for display and delay function. Then communication for RS-232 and Ethernet are tested. Then we have tested that CPU card with IO modules, the digital input and output, analog input and output card. These cards are designed and developed in EID. Then we have ported the NNS application and tested. Then SRS application and tested. Then we are testing this core with some test benches. This is the typical setup. Typical reactor application software successfully ported in the CPU card and tested by simulating the field inputs. This is the SHAKTI processor and this is the Modular processor. With the switchover logic, we have tested the application software. Functionality and performance of the CPU card is evaluated with the existing CPU card. Then with that confidence, we have designed and developed the full-fledged CPU card version 1.0. VME bus-based CPU card is designed and developed, then ported the typical application software and tested. This card is not having any piggyback board. Then deployed in the field. This card is field deployment of SHAKTI processor-based embedded system. A data acquisition system based on SHAKTI CPU card is deployed in electrical substation at IGCAR. Data is continuously monitored and logged for future reference. This is the IGCAR roadmap and our achievements. First, that piggyback board is designed and developed, then tested, then full-scale verification and proof of concept by porting the majority application done. Then we have developed the version 1.0 board without piggyback board. Then next step is development of SoC based SHAKTI CPU card. This is the team members from IGCAR. Dr. Tirunyanamurthy, he is the leader for this project. Then myself and Manimaran, then Mr. Satyarajesh Medidi and Mr. Anil are working with IIT team with Professor Kamakodi and his team. Thank you for the opportunity.
Thank you, madam. Thank you for our highly technically condensed talk, which is covers our reactor safety critical system, safety related system, non-nuclear safety system, a computer-based INC system, how it will be involved in that process selection, design development methodology, and IO core based processor, how we are selected, what are the characteristics needed for this, and obsolescence of electronics in the component life, very clearly explained, and the mitigation plan also you are justified how we are mitigate that problem in near future, and more than one vendor we are identified and no bug also identified in the these are the criteria. What are the criteria needed for selecting the processor you are clearly mentioned, and free and open instruction set architecture of SHAKTI core variants, and C-class embedded system also which you are developed and which you are running in the SHAKTI processor. Also, you clearly explained with the help of the architecture and workflow in the RISC-V system, and verification of the C core also you are clearly explained, and MC68020 replacement SHAKTI piggyback board, how we are developed initially, how we are accommodating the SHAKTI processor in our existing system. In observations, whatever you are made, and then how we are slowly transformation happened in the piggyback board to actual board. And you are fit into that VME bus-based CPU card. That VME bus-based block diagram clearly explained, and two processor, co-processor, and the main processor are replaced by the SHAKTI processor by the actual VME bus-based CPU card. Then that also Amir Raza, one minute, Amir Raza. Functional testing of SHAKTI CPU card, porting reactor applications of SHAKTI processor how full-fledged CPU card testing is going on also very clearly explained in the application of electrical substation of IGCAR, and you are continuously getting the data, monitoring the data, acquiring the data, and the output you are comparing with the existing inputs. So this is a innovative technology which we are slowly implementing in the advanced pioneer system of our reactor instrumentation INC system. Thank you, madam. Thank you for
Thank
your
you.
valuable time. Any
Thank
questions,
you.
please? Any questions,
Yeah,
Basha?
yeah. Hello, hello.
Please.
This
Yes,
is
sir.
Shanmugam.
Yeah.
Sridevi, nice presentation, and it is very good to see the indigenous achievement. I'm curious to
This is
know
a
whether it
teamwork,
is
not indigenous.
no, indigenous. I did not say
Okay,
individual,
okay.
indigenous.
Individual.
Okay,
Is
okay.
it, recognized under Make India program?
Yes, Shanmugam. Yeah.
Oh, congrats.
Professor Kamakodi is trying for that because this processor is indigenously developed, no, by IIT.
Mm. Mm.
So they are on the way.
Okay, congrats.
Thank you. Thank you.
Any other question? Basha? Basha? Basha, please. No more question. Thank you once again.
Thank you for the opportunity. Thank you for everyone.
Thank you, man. Thank you, man. Thank you.
Thank you, sir.
Thank you. Next speaker is Joseph Winston. He is explaining about the robotics application in nuclear reactor, how we are selecting the robotics component and how we are applying into the fuel handling. I am inviting Joseph Winston, please. Joseph Winston. Joseph?
Yeah. Am I audible?
Audible, Joseph. Video also you can switch on.
Okay.
Video also. Video you can share the slides.
You're able to see this?
Yeah, now it is shared. Shared. Thank you. Thank you, Winston. Good evening once again, engineers. Engineers, today we are going to see about the second talk, development of remote inspection technology of reactors with the help of robotics by engineer Joseph Winston. I am hand over the mic to Joseph Winston. Joseph Winston, please. Please start.
Yeah, thank you, Shanmugasundaram. Good evening to all of you. I am very happy to be part of this engineers forum today. And my title of the talk is Development of Remote Inspection Technologies for Reactors. So in my talk for 40-45 minutes, I'm going to take you through one of the inspection system development which has been done for the steam generators. So particularly what are the various things which were factored into the design of the robotic system for the inspection, comprehensive inspection of the system. That's what I'm going to talk about today. So my prime focus will be on one particular device so that we will all have a good awareness on a particular system, what all need to be factored for a inspection tool. So first, the prime objective of most of the inspection system development is one, always we keep in mind for the remote deployment. Apart from the inspection functions that are being factored into the design, we also have to look into the design of making systems completely remotely deployable, which adds up a lot of engineering into the system apart from the main robotic system. So this becomes very important to have a remote deployment system. Many auxiliary systems get added to the main system. Then the payloads, particularly for this inspection tool developments, we primarily focus on putting the NDE tools like UT sensors, like ultrasound sensors, then the vision tools, cameras. And if it is being used in the radioactive environment, we use highly radiation resistant cameras, which can see up to 500 kilo rats per hour. So such cameras need to be put. Otherwise, normal cameras, what happens is the lens will get darkened, as well as the CMOS sensor, which is present in the camera, also gets affected due to the radiation effects. And often require self-localization and self-calibration. This is one of the very important things. Conventional robotic systems, whenever it is deployed outside, the system takes a reference from a known point. Or particularly if the robotic system is going to do a measurement, so external laser-based calibration systems are used, or some standard scaling, which is a multi-dimensional scaling way it can be calibrated so that the system can function with ultra-high precision. But particularly when we go for this reactor technology systems, we need to remotely deploy. And once it goes into the target space, we do not have any kind of external reference tool deployed into the robotic workspace. So the robot has to self-calibrate. It has to do the self-localization. So primarily what we do is we used to use some markers in the target workspace or a kind of standard dimensions, whichever is possible on the workspace where it is being deployed. And if nothing is possible, we externally, that means we add a calibration system into the robotic system. So once after deployment, it does a localization and self-calibration. See, for example, when the robotic, if it is a remote automation vehicle system, if it has to move, the vehicle wheel odometer is taken as a reference for its localization. But after being operated for some time, due to the wheel slippage by excess torque and the kind of additional loads that are coming on the system, the encoders might be giving a false readings. So we need to keep on correcting the system based on the references which are available in the target workspace. So this is one of the very critical aspect during the inspection. We keep on doing the self-localization as well as the self-calibration of these remote tool systems. Conventional systems has a very good laser-based referencing tools which are much easy to deploy, but particularly for the reactor applications, this needs to be done in a very sophistical way such that it can be calibrated in a remote location. Only then we can get a high precision data collected from the target workspace. And another important factor which we consider is the hostile environment. So you can see the temperatures are typically very high where the systems are used. So primarily when we design such systems, we look for motors which are resistant to high temperatures. It has to be the sensors which are put on the robotic systems have to see high temperatures. Wherever possible, we go for a high temperature resistant systems. But however, if there is unavailability of these sensors and actuators, we try to cool the system by means of external flow of nitrogen, chilled nitrogen, and cool the system and make the system survive in such hostile environments. And wherever radiation effects are there, one is applying a shielding, or we can use RR radiation resistant sensors which are being used for the applications, particularly when there is a motors and other thing. Motors generally survive, but the encoders which are present on the backside of the motor to see the revolution counts, the encoders, the electronics on the encoders often fail. So we go for resolvers. Resolvers are without much of electronics in the system, we get the position reading through the resolvers. So these are some of the aspects we factor into the design so that it can survive these hostile environments. Then we need for vision processing and augmented reality. Whenever we go, the target space is already from the design, we know the kind of neighborhood systems. So we just name them on the vision processing system through standard vision processing libraries, and we inject the text into that and then mark those locations, which makes the system more user friendly for the user when he is operating on remote locations. So particularly on this talk, I'm going to just present only one of the developments which we have made. Maybe in future we can look for other systems also. Here I just would like to comprehensively cover what all the aspects which have been taken into the design of the steam generator inspection system. So my talk today will be primarily focused on this system only. And particularly on this, various aspects which were considered, like modeling, simulation of remote inspection robotic system for steam generator inspection. So first I will just cover about the steam generator parameters, so that how complex the system is, and also to sensitize what is the scenario, international scenario on this particular heat exchanger inspection system. And then the conceptual design, how this was evolved by the fundamental operation methods. What are the various operations needed to inspect a steam generator, which is a heat exchanger. So primarily there will be, the moment we say it is a heat exchanger, mostly shell tube heat exchangers are commonly seen. So the tube, particularly in the reactor application, the tube side, high pressure water is present, and the steam gets generated, which is at very high pressure, which goes for the running the turbine, and then the power is generated through the generators. So these inspections are to inspect all the tubes for any kind of flaws, if any, and to isolate the tube from the service. And another important thing which I would like to cover is a modular design. Whenever we go for such a robust system designs, we break down into smaller modules based on the conceptual design. Based on the conceptual design, like how to deploy the system, how to expand the system, and how to make the system functional, and how to do the inspection, and how to retrieve back the system and come out. Based on the basic concepts, the system will be modular way, it will be designed. Like deployment means there will be a deployment module which will push the robotic arm into the system for the inspection. Then the robotic arm will perform orienting the tubes, and the cable and the probe pushing will be done by another module. So what I would like to emphasize here is this much of the robust engineering systems, once it is broken down into a modular design, it becomes much easier to handle such complex systems and to discreetly qualify the system for service, and then integrate the overall system and see the overall performance and qualify the system for the actual application. Then auxiliary setup arrangements like device assembly, service, dismantling, how to carry out the service of the equipment, and before deploying the system into the actual required target space, we need to do all kind of assembly integration and also to carry out the service in case of any replacement of the motors. Such robust systems need good support arrangements and good service platforms through which this can be taken care of. Just like when a car is moved into a service stations, you find a lot of handling systems and also the service tools which are present to carry out the necessary services. And the final is the qualification of the system before actual deployment, so that the regulators are happy with the kind of design intent being met by the qualification of the device. And once that satisfaction is achieved, the system is put into the actual use. So in this particular case, I would like to just emphasize why are these inspections first important. The need for inspection is water is there on the tube side, and shell side sodium is present. In case if there is a breach of tube, this water and sodium will mix, and it will be a highly exothermic reaction, which will cause a kind of a very violent reaction, which will cause neighboring tube also getting damaged due to this sudden pressure variations which are brought inside the line. So this need to be properly inspected, and well in advance, this healthiness of the tubes have to be identified and also put in service such that they never cause any kind of accidents. So that is the primary intent of the design of the inspection tool, so that they are performing to check all the tubes and then to qualify the steam generator heat exchanger in the service. So in this particular case, you can see here in the PFBR layout, this is the reactor vessel, and the sodium comes, the reactor heat is transferred through the sodium, and it comes to the secondary line, comes to the heat exchanger. So here you can see the steam generators which are present here, 3-4 steam generators on one loop, and another 1, 2, 3, 4 heat exchangers on the other loop. So these are the heat exchangers which will remove the which will take the heat of the sodium, and then water gets converted to the steam, and the steam comes out. This steam goes and runs the turbine for power. So you can see here from this layout, they are all pretty tall structures. So you can see it is about 25-meter tall structures. It's about a 10-story building roughly. So you can see that the tubes have to run all this inside tube sheet to tube sheet. It will be about 23 meters. So these tubes are very small in size, and at the same time, this need to be inspected by proper means. So here to blow up the image, I have put the steam generator here. You can see here the secondary sodium enters here in the shell side, and the sodium comes out. So particularly the high temperature sodium enters here and then exchanges the heat with the water in the tubes. There are 547 such tubes running from bottom header to the top header. So you can see that water enters here, and there is an access port. There is an access port here. Generally, it is closed, and the steam comes out. High pressure steam comes out. So for thermal expansion, bends are given here because of thermal difference in the thermal gradients across various tubes. There can be differential expansions. So it has to be accommodated during the service. So the flexibility is given through a thermal expansion bend. So the only option available is to deploy a system from the top or to deploy a system from the bottom access port. But the bottom access port is not possible because flow control orifices are put here in all the tubes at the bottom. Flow control orifices are put here. So any probe cannot go inside the tube here. So the only option is, next is to deploy a tool from the top and to push the cable and the probe all along the 23 meters down and carry out the inspection of the tube to tube sheet weld here. Tube to tube sheet weld here and also tube to tube sheet weld here. These are vulnerable spots where primarily the cracks can propagate, or during the weld there can be a kind of a flaw which would have slipped through, which can propagate to failure. So primarily these are very important. And apart from that, the full through tubes are to be inspected. So a tool has to be deployed after removing this manhole at the top, and this robotic system has to go here. And here, as I told you, 547 tubes, they all stand like holes here. So through the tiny hole, we have to push the cable all the way down to the bottommost point to inspect this also, while it is doing the inspection along the tube, full length of the tube. So in case of any kind of abnormal signals coming out of eddy current, normally eddy current systems are used. And this is a ferromagnetic material, so it has to be a remote field eddy current technique. So there will be a primary coil and a secondary coil. And when the primary is excited, the phase difference is considered to be the flaw indicators. So there will be a continuous plot between the phase difference between the primary and the secondary, which will give an indication for the inspectors to understand if there is any abnormality along the thickness of the tube. If there are any abnormality in the tube, it can be identified from the remote field eddy current technique. So this calls for a kind of a complexity. Like suppose if you see an average human being, the shoulder width is about 450 millimeters, whereas in actual case, the access port is only dia 381. So it's very difficult for a human being to straight away go here and do the orientation to the particular tube for inspection. So there'll be an array of tubes starting from here and running 23 meters down. So that calls for a robotic system which can be deployed here and uniquely identify all the 547 tubes. And the further complexity is, if you see an inspector sitting here, in this case is a heat exchanger which he has a good access to the tube sheet. So here at least he can use a chalk piece and try to mark whichever tube he is inspecting. He will put a mark and say this is inspected. And also he can have a numbering scheme and then say that this tube is inspected, this tube is inspected, like that he can make a marking. But in our case, the biggest challenge is there is no indicator available here. That's why I said self-localization and also self-calibration is very, very important. In the few slides later, I would just explain how important these calibrations are for particularly precise operations of these kind of inspection tools when it is deployed into the reactor systems. If you miss out one of the tube, we will be wrongly marking a tube that in case if there are some indications coming out, we have to clearly tell on which tube these indications have come. So those aspects are very, very important, particularly for this kind of systems. So here you can see the system, this is the flange where the dummy is removed and the system is mounted here. And this will be the robotic system which is deployed into the manhole, and then it will go and position the probe to each one of the tube for pushing the cable into the tube for inspection. So one thing one has to note here is the tube position is numerically controlled. There is no manual intervention or there is no manual jogging to reach the point, because literally impossible for human being on the loop to position a tube, because once you look through the camera, you can see here that CAD model shows there is this one, there are so many tubes starting from here, 547 tubes starting from here running down. So all these are tubes. So there are 547 tubes. So literally manually orienting to a particular tube is near to impossible. It is not possible at all, except that outer row tubes can be identified. At least there are some V patterns through which one can identify that this is a particular tube. So our calibration systems are so powerful, which we have developed in-house calibration algorithms, which will take help of this V pattern and does a self-calibration. And later on, it is almost like a bullseye hit. If you go to a particular tube, it is exactly the tube center on which the probe is positioned. So here, you can see here the international scenario is in PSWRs, there are many players who are doing the design. There also the tube sheets are there, where there is a tube runner through which the probes are deployed, and then that pushes through the steam generators in PHWRs. But in the international scenario, we are the first to develop one system for the fast reactors, which is PFBR steam generator inspection system, PSGIS. And that has been evolved through a conceptual way of design where, the manhole is closed here. So once the manhole is open, initially before opening the manhole, the water is drained through this feed tubes, and the sodium is also drained, and the system is completely purged with nitrogen. And once it is purged, then we open this for the inspection. This will be open for inspection. And we mount the device on the top. You can see the flange is now mounted with our device on the top. So once it is deployment operation, the robotic arm, which is housed inside, nicely housed inside, need to be deployed into the system because it has to expand and reach up to 850 dia, whereas this is 381 only. So the configuration of this funny bend and all things are designed such that they can compactly sit on the manhole gap in the hole, and later on after deployment it stretches. See, here you can see the device is deployed now. Here it is deployed now, and the robotic system is still in the folded condition. Then it expands and it can reach up to the outermost tube also for inspection. Then once it goes to the particular tube, the cable pushing is done. So that means the probe is pushed down through the tube, and the tube diameter, keep in mind the tube diameter is only 12 mm, 12.6 mm. It's a very tiny tube through which this probe has to go down and then negotiate this bend and reach up to the bottom, raise to spigot weld here and inspect this and come out. So the biggest challenge is positioning, which is called as tube location operation, and then the ECT probe pushing into the SG tubes. So these are the conceptually evolved methodology of the inspection through which the systems are now designed based on this. So we have a cable take-up system at the top, and then the cable dispenser module. The dispenser module is nothing but it pulls the cable from the take-up, and then there will be a pinch roller which will push the cable inside. And this will come to the tip, and here there are another two pinch roller which is called cable pusher module. Cable pusher module, which will push the probe and cable down. And these are the two arms which are folded and kept, and then once it is deployed, it expands to orient to various this one. Primarily that we call it as tube locator module because it locates the tube for inspection. Then the device deployment module is the one which deploys the entire robotic arm into the header, and once the operations are over, the arm will be folded and then taken back into the shroud tube. And once it comes into the shroud tube, the entire device can be decoupled and taken out. That is the way the full operations are being done. So we have two ways of doing the inspection, that is eddy current probe and analysis system that will do the tube volumetric inspection. And we also have VPAS, that is vision probe and analysis system. That means we had to develop a miniature camera probe which can go into the tubes for inspection, collecting vision images, and then come out with the tube inside tube views. Then we have the comprehensive control system. As you have seen here, each one of the concepts which are put here needs actuators, which are electric actuators, which are used to deploy a system, mechanical system, by running a motor and putting the deployment operation to keep the robotic arm into the header. And tube locator arm system, there are two motors which are performing the task, and cable pusher module and the pro pushing has 4 motors. All these, there are a lot of intricacies in these things, which I'll explain in the next few slides. So as I told you, the tube locator module is the most complex and precision robotic arm. This is the robotic arm system where a 2-axis human hand like a robotic system will be deployed into the header, and that operating the 2 motors, you can orient to all the 547 tubes. You can orient to all 547 tubes in the tube sheet and push the cable using the pusher modules. Then the complexity here is the development of inverse kinematic algorithm, where it is a completely numerical technique. And apart from the development of numerical algorithm, the biggest challenge is stability of such algorithms. Numerical instabilities can come whenever there is a division by 0. Particularly, these are matrix-based algorithms. When the determinant becomes 0, the invertibility becomes a question mark. So we have to use some techniques like damped least squares technique to avoid numericals in singularities. All these have to be taken together. Otherwise, what would happen is suddenly the motors will see enormous current due to sudden accelerations of the motor system, and the currents drawn will blow up the fuse and completely halt the system for a while unless you reset everything. So numerically, it has to be handled. So all these developments have been well taken care of to see that there is no instability comes on the numerical algorithms during the actual inspection time. So you can see the deployment operation is again another motor which will be pushing the system, mechanical system, and the cable management is taken care by the cable management. Then the pusher module and dispenser module are 4 motors which are taking care of drawing the cable and pushing into the cable. Then the inspection primarily is done by, as I told you, ECT, RF, ECT or VPAS, which is vision-based data collection. And then finally, the system integration into a single unit and control the entire system by means of a distributed control system. So this way, when we design the system, so here you can see it is a simple mechanical system with a ball screw arrangement at the center, and there are slides, LM slides, linear motion slides on the side, which will support the deployment system for accuracies. And top, there will be a motor which is running this ball screw, which deploys, causes the forward motion of this deployment and then pushes the robotic system into the header. So that is done by the deployment system. Then the tube locator module is the robotic arm. See, here you can see the complexity of the 2-axis robotic. Here there is a motor and here there is a motor. And these motors are working with the encoders, which are very high resolution, 5000 PPR with the quadrature, and also 200:1 gear ratios. So it's somewhere close to 2 lakh counts. 2 lakh counts we get for 1 rotation. So it is very, very high precision motors, and they are particularly called as harmonic gearboxes are present in the motor. Along with the motor itself, the gearbox, encoders, everything are integrated into a simple compact system. And these gives you almost a backlash error of only 15 arc second. That means normal gearboxes will have a few minutes error, which will cause a lot of positioning errors in robotic systems. So we go for this ultra high precision motors to precisely orient to the tubes. So that is the most important part of it. And also here in this entire system, here there are 2 servo drives, tiny servo drives, and here 1 servo drive and here 1 servo drive. So all these servo drives are interlinked by the CAN communication protocols, and the integrated program is done on the control panel. So the control panel will have a layout here, you can see, which is similar to the tube sheet having the holes. The operator touches the particular tube, and the say execute, then the arm unfolds and goes to the particular tube of orienting to the tube. So this developments are also electronically controlled through the distributed control system with the motion controller, interfaced with the HMI screen through a field bus, mod bus, and then based on the inputs that are taken from the HMI, the motors are run to position the arm. Then the development of pusher modules, testing discretely, see cable pusher module and cable dispenser module discretely tested and pushed into the integration of the overall system. Then finally the RFEC system, which will acquire the data from the tubes when the probes are moving into the tube. So prior to the deployment, we put the RFEC probe for calibration in calibration tubes. These double peaks are typical symptoms of the, see, actually it has been put into the calibration tube, which has a prefabricated flaws. So based on the amplitudes that are seen, the system gain factors are set for and calibrated for the actual use of the RFEC system in the actual case. So here, if you see here, what of the complexity which is involved in the cable dispenser, see the cable is drawn and then pushed into the tube here, and there is a sheath which takes up to the end, and here there are two motors, and here also there are two motors which are running. So normally when the traction force delivered is higher and the cable is not drawable, then what happens? The cable slips. So what we had done is we have put an idler encoder. So idler pulley, and the idler pulley has the encoder. This idler pulley has the encoder, and this active pulleys are attached with two motors, which are running in one clockwise and anti-clockwise direction, so that the cable is pushed inside with the force. And we need to continuously monitor the torque of these motors. Otherwise, what would happen? The feed rate will be at an angle. So this will cause a lot of additional frictions. So we need to avoid such this one. Second thing is there should be speed controlled. This motor, cable drawn, and the feed rate is less, there will be slag. There will be slackening of cable. And if this motor runs faster and this motor runs slower, then there will be a tension. Using a master-slave configuration, master-slave configuration, we are controlling only one motor. We are controlling only one master. If you see, this will be the master motor controlled, and the simulated encoder output is fed into the second motor, so that when you run this motor only, this will command the second motor. But the signal is inversed. That means clockwise and anti-clockwise is generated. Then this in turn comes and controls the other motor here. And this also clockwise. So that means what I would just tell here is, if we miss out controlling these motors discretely, we'll end up in cable tensioning or slackening of the cable. So we have a completely master follower which takes care of this in a digitally coupled manner, electronically coupled manner, such that whatever the speed at which the operator is running the motors, they are all self-adjusting themselves to see that there is no slackening, there is no additional tension generated. So, and also by simple torque by pulley radius, we find out the cable force, and based on the motor current, measured, we keep on tabulating these values on the screen, so that motor 1 and motor 2 should oppose each other and give a neutral value. If there is leaning on one side, we understand that there is a feed rate is wrong, and simply we find out what is the problem. We have to take it out and then reset the pulleys back and then put it to service. These are good indicators in live inspection time, which will help us to identify if there are some abnormalities in the system. And based on both the motor current, we also estimate what is the cable feed force. So that will be indicated in this graph, which will give us a good indication that if the tube, once the probe is going into the tube, there are frictions which are playing actively, which will oppose the motion. So that will manifest in the form of the additional force requirement on the pulleys. So if it exceeds certain limit, we understand that the probe is getting excessive force due to friction. Either it may be a block or it may be due to some kind of rubbing against the wall. So we identify these things by directly from the control panel and do the necessary service corrections to put the system back in service. And also we get the RFEC data on the HMI screen, and this complete program development is done in-house, mechanically interfaced, and then electronically controlled. And also we have used, as I told you, once the ECT cable is removed and vision probe is put, then we can view the internal camera using a camera. You can see here a small miniature board camera is used, which has a diameter somewhere close to dia 6 is the diameter of this camera, and there are LEDs here, LEDs. So this is housed inside a PVC. We internally in-house fabricated this and pushed this tiny miniature camera using the same feeder system into the tube. You can see some of the views which are present seen here. It has gone up to the bottom and it is inspecting the bottom orifice. And these are diameter 1 mm. So it is seen through the camera in the control panel. Once these things are pushed into the tube, you can see the bottom orifice at the end of the tube. So continuously this vision inspection can be done by this kind of system. And also other cameras which are supported at the where the probe is extracted out, you can see cameras are giving a very close-up view. These are the close-up views which the operator sees at the screen. When the positioning module brings the cable probe to the top, you can see that the precision it has will be good. Normally, we keep a clearance so that it doesn't interfere with the tube sheet during the movement of the arm, robotic arm, while positioning to different tubes. Then we push the cable and the probe down through the holes, tubes which will run 23 meters down from this point of insertion. And some of the controls you can see here, as I told you, deployment module has a motor here. There's a motor here, and tube locator module has two ultra high precision motors. And all these are connected on a CAN bus network. And the protocols which we are using primarily are various protocols like CAN DS standard. They're all motion control standard, the standards which are being used by us for programming the system for controlling each one of the servo motors. And the field bus, mod bus is used for communicating with the HMI which is present here. You can see the HMI here. And the motion controller which is put on the panel of inside the panel of the control panel. And the vision system gives the video stream coming to a display panel at the top. And there are DVRs to record the system. And primarily, we use the ladder programming, functional block diagram, structured text. These are IEC 61131 Part 3 coding format, which is standard for open PLCs. And that is what we have been using for interfacing all the electronic system into one network and then bringing everything to a HMI interface through a Modbus protocol. And this helps us to reduce the number of cables running from the inspection system to the control panel, because the CAN bus is only a two-wire communication, and then the power bus runs. And with that, we will be covering up the complete electronic controls of the system. And then we are using the open standard. So no matter what the servo drives and the HMIs are brand-wise, they are different. But we try to choose open standard so that all are interfaceable through the same program, which is uniformly covered through IEC 611 Part 3. And now I will just explain some of the complexities on the machine intelligence which has been put into the system so that it operates at a very high precision, and also less skilled manpower need to be deployed for such things, because it's a complex inspection process. You can see here the tubes. These are the actual layout simulated through a Python program. So many tubes, 547 tubes, 547 tubes, which are simulated and shown here. And as I told you, it's a 2-axis arm. This is one arm and this is another arm. So at the tool tip, this is the place where the probe will get pushed down. So in order to reach a particular tube, these two are very important. This angle, θ1 and θ2. So we are using an inverse kinematic algorithm developed in-house, computing the Jacobian. All our matrices which are coming in real time, which are programmed into the tiny motion controller. In that IEC, it's a 611 part 1, part 3 format. So these matrices so happen, since it is a 2-axis, it comes 2x2 matrix. So inversion, everything is much easier because you can directly interchange the diagonal, off diagonal elements, you can interchange and change the sign and do the inverse. Otherwise, computationally, this becomes more trouble for motion controller to do the iterative process and get into bigger numerical troubles during the actual case. So that is why often we do this process. When the operator says execute, we do this computation and come out with a solution. And then first we say the IK process. Once that process, in fraction of seconds, it comes out. Then we say execute. That means it moves to the particular tube. So before that, all the convergence checks, everything will be done. So the motors are in a very comfortable way they are run. Otherwise, any kind of abnormal current will cause the system to trip and then cause so much havoc in the system. So they are well taken care of during the numerical control of the system. That is where we are using the damped least squares technique. This damping is the factor which is controlling this kind of abnormal singularities. This particularly happens when the arm folds. If the arm starts folding and it comes below this, then the singularity will happen. So suddenly the accelerations start coming in, and that will draw the torque requirement will be enormous, and that draws more motors will start drawing more current. So this inverse kinematic algorithm is completely stable, which has been proof tested by various simulation techniques. You can see the velocity. Actually, interestingly, the most challenge which is coming on running the motor, normally people run the motor on position control, but we are running the motors on both position and velocity. Velocity on the inner loop, velocity on the inner loop, and position on the outer loop. Position will give the reach accuracy, and the motors have to be controlled on a profiled velocity. Only then the arm goes in the shortest path. If the arm has to go from this tube to another tube like this, motor speeds have to be in a non-linear way. Only then we can bring in a linear way output function. That is taken care through the kinematic algorithm, which we have developed in-house. And interestingly, finally, to pump this data into the motor, we go for that position velocity time control. That means position velocity. That is why I said velocity on the inner loop and position on the outer loop. Only then we have a precise control of the system. So this video you can see here, where from the control panel, when the operator says enable the motor, the 2-axis motors get enabled, and then the tube sheet layout will be presented to the operator. And this is doing the homing now. This is put on the test bed now. Right now it is on the test bed on a study bench. Once these calibration algorithms are tested, then we put it to the actual system integrating with the actual machine. So you can see there is a tube sheet template which is printed on a A0 sheet. And you can see the same thing is simulated on a HMI screen. Then when the operator gives the actual tube designation, then execute. Once he gives the execute, the arm IK execute will make the arm move to the tube. Now you can see the arm moving to the tube, particular tube. And in the control panel also, these vision systems will give the tube below that. So before putting into the actual system, we thoroughly test these algorithms in Python scripting for convergence and also for the numerical stabilities. Then we finally port into the machine, because finally when we put into the motion control programming, any kind of uncertainties on the schematic will cause a kind of abnormal function of the motor. So we need to precisely control, check all the converged values before putting the values into the motion control. So that will be extensively done through this. And here, this is what is another major challenge. Actually, once you deploy the system into the manhole, there is no guarantee that the base of the system is always at the center. So the system can come with an offset standing here like this. So that means if you theoretically run here, it may stand offset. So we are doing a 3-point calibration. See, this V pattern is prominently seen in the actual setup. You can see here, there are 6 number of such V patterns seen here. Every 60 degree, you find these V patterns prominently visible. Then we move to this 3 of the widely spaced V pattern, where this root tubes theoretical data is available, XY coordinate value. Then we have incorporated, this is an in-house developed singular value decomposition algorithm, where we do a estimation. See, all these locations, we measure the error function. So this, after doing this 3-point calibration, we get a matrix which has a rotation elements and also the translation elements. This is 1, 0. So we will have a rotation elements as well as translation. So any tube under inspection, when the operator wants to go here, first we take the theoretical XY value, then we multiply with this translation matrix, find out the error position, then we run the motor to the error position, which means that we don't do the correction of errors by manipulating the device, but rather numerically we correct the error after the 3-point calibration, which means we live with the error, but do the on-the-fly correction. We do the on-the-fly correction, which will make the system ultra-high precise reach of the tubes in the tube sheet. And with this some data, you can see that this is one of the actual data. The tube sheet V pattern has gone rotated as well as translated. So this much of error can cause a tube, 2 tubes. The pitch is 32.2. So as high as 60 or 64 is the error. So instead of standing here, the operator may wrongly go here if you don't do the calibration. So when you do the calibration, these are the rotation matrices, translation. When we apply this, automatically the system will go to the correct tube position for inspection. So this is the essence of doing this calibration. As I pointed in the first slide, it's very important that these kind of localizations and this kind of calibration have to be remotely done. There is no access. Once you see here, once you put the device here, it is completely closing the manhole. So the device is going inside, where the operator can see everything through the control panel only. So he has to depend on remote calibration, remote localization of the system, which is done by these intelligent algorithms which are pre-built into the system. These are all indigenously developed and put into the machine code. And only difficulty that we have faced here was this SVD is a very complex matrix algorithm, which we could not, frankly speaking, we could not port it to the motion controller. So through TCP/IP, we pushed this data to a Raspberry Pi system externally brought near the actual calibration equipment. And once the data comes into the Raspberry Pi system, then we are doing a Python scripting, which is done on the Raspberry Pi, which is using a linear algebra library of Python, which is a single line command to do the SVD. And once the SVD is done, this matrix will be again pushed back into the motion controller. Once this data becomes available for the motion controller, then the motion controller takes over for precise operations. Now, this is another algorithm which we have powered in. Like randomly, we need to inspect some of the tubes. If the operator start jumping between the tubes, it will be like a drunken man walk. It will take a lot of time for completing the complete inspection. But whereas we run a genetic algorithm, but only caution is it takes a bit of time. This is done on offline. Then we converge on the optimal schema. And this is loaded into the motion controller for sequencing the tube inspection, which will be a very structured way. which is genetically evolved. But this is run on not on real time, but in this offline way. And the obstacle avoidance, whenever there is a tube which is plugged, the arm should not overlap the plugged tube for safety, because the probe should not hit on this, or the arm should not hit on the plug tube. So whenever the operator chooses from one tube to another, this will ensure that it will generate a via point. Through proper planning, path planning, it deviates and takes a detour and reaches here. These all things are done in the system level, where the operator need not take, all he has to do is load the plugged tube locations only. Rest of the things will be taken care by this. Then the Kalman filter, anyway, I'll not go into detail of this aspect, because this is again a higher order of algorithm, where when the operator keeps on, even after calibration, there may be a slight offset error. Even after calibration, there may be a very slight. I have magnified and put here, but this is very, very less. It will almost go to the center, but it will be slightly deviated within the tube. So whenever operator does a little bit of jogging, this predictor corrector method we incorporate. This is yet to be launched into the system. We have done the case studies and proved that it matures over a period of time, so that the error correction jogging becomes lesser and lesser in the due course of time of inspection. So this on a test bed, this is being tested. Whenever there is a variation in the tube sheet, like a tilt, I exaggerated and put this is the actual tube sheet. When the device is operating on a different tilted way, this keeps on getting corrected by the first is 3-point calibration. After that, this error correction by this method. And another very important thing is, whenever the arm overlaps, as I told earlier, this arm, when the operator gives a point which is passing through this center and goes here, this arm will overlap each other. But if you see here that the inspection cable is taken out through a hose. So this hose will get stuck between the arm, and it will cause a local accident there. So it will cause a local accident there. So we should not allow this to happen. So we thought of putting a simple way mathematically. What we did was we evolved a circle, a virtual circle at the center, and never allow this end tip to pass through this center, this virtual circle. What we do is, whenever the operator gives, he's standing in point A and he has to go to point D, it does a tangent to this virtual circle, find this point, then go along the curvature, exit tangent from this, and then go out. There are two possible ways. This here also you will get a tangent. This also is possible. But we find out the length, and lesser, for reducing the duty cycle, we choose the lesser path and go through this. And this is one of the simulation result, where we try to randomly choose points and made the system to run for some time, so that it never crossed the virtual circle at the center, to prove the strength of the algorithm. This also yet to be launched on the actual system, but it is at the system simulation level right now. This will be soon ported into the actual system, so that even operator gives a diagonally opposite, the system will automatically take a detour and it goes to the other end. And these are auxiliary systems, as I mentioned you, for the service. The device need to be put here, and then there is a tube sheet, and all this calibration, demonstration, everything are done out of pile, and then it has been demonstrated and qualified, and then later on it goes for the inspection. Second thing is, this stand will be used for the service also. If you want to dismantle the system and do the servicing on that, this can be put on the test bed, and then this is done. So what I would like to emphasize here is, first, the mock test one, all these algorithms are put on a test bench and everything are qualified, so that it is completely foolproof. Then second thing, in an integrated test, where ECT system is also integrated, and then it is tested in this dummy tube sheet. Then the actual service support structure, the shroud tube is taken. Actually, there is a shroud tube which will protect the robotic arm. And this is a control panel on which the camera images come here. And this is a HMI screen, where it is a simulated tube sheet comes here. The operator touches the tube or enters the value of the tube number. Then the system moves here. So this everything is proof tested on a Mark 1, Mark 2, Mark 3 test setup, because it has to rigorously tested prior to the deployment in the actual system. So once this 1:1 markup also, not the actual steam generator, but simulating the full length, everything, it is mounted here and then pushed to 23 meters. That will be the final Mark 3 test, and then finally gets qualified for the actual deployment. So after the deployment, this is the actual steam generator. You can see here, this is a top flange, thick top flange, and the device sits on the top, and the cables come out here, and we have no clue what is happening inside except for the screen images where the probe you can see here, and the HMI screen through which the controls are done to run the motors. So there are about 8 to 9 motors which are running on the system, but effectively the most critical is that 2-axis robotic arms, so 2 motors which are run on a synchronous way. Other motors are discretely run, which are much easier to control, So this is a folded arm. You can see here where the inspection probe comes here through this tube, and then the probe stands here. After the deployment, this is what unfolds and goes into the actual, this one. In the CAD model, you can see here, this arm gets stretched out to the tubes for inspection. This is a final for this deployment in the actual steam generator. You can see the manhole is opened here, and it is in the temporary structure. Then this is lifted and put into the system. Then the controls, operator completely sits on a remote control panel and does the control of the device. And then the RFEC is secured in the RFEC station nearby, and the data collected for all the tubes, so that the tube healthiness is checked in all the tubes and qualified. That is the way finally the device goes for. See, these are some of the images which have come out from the tube sheets where the probe goes very close to the tube. See, apparently it looks small, but the probe goes inside the tube. This is the diameter of the tube, that is 12.7. You can imagine 12.6, which is very tiny tube and running 23 meters down. So the probe goes here. See, you can see the clearance, it's very small. And this is a secondary coil. Primary coil has gone inside in this image, and this is a secondary coil going inside. See, if there is some eccentricities, like this side gap is more, so there may be rubbing here. So the operator prior to this insertion does a slight jogging to correct. See, the numerical control is completely done by the system. See, all these tubes are designated with some number, row number and the tube number. So row N, H. So now we are developing vision-based algorithms to create augmented reality, which will create, it will put the numbering over the tube. So the operator will get a feel what tube he is inspecting. Right now, there is no marker available, numbering scheme available in the tube sheet. So we emulate it and put it on the screen so that the operator gets a complete feel of the inspection environment. I think with this, I'll just close my talk. If there are any doubts, I think probably questions may be asked. I'll be happy to answer.
Joseph Winston, shall I ask one question?
Yes, sure.
It is already patented?
No, patent we are not done yet. We wanted to patent it, yes.
Okay.
Because a lot of machine intelligent algorithms have been put into the system, yes, which makes it more intelligent.
Yes, it is a world.
Yeah, first
approach you are taken, no? So
yeah,
that's why I asked this question.
The first reactor.
Yes. So many systems you are developed, and a lot of engineering aspect also mixed up and then flowered in your task. Cable take up module, cable dispenser module, device deployment module, tube locating module, cable pusher module, inspection system module, vision probe module. Always you are all these modules and all these operations, you are identified that tolerance.
Yeah, everywhere we see it, suppose if you take the tube, reach, if it is slightly deviated, only thing is it should not be more than the tube diameter, because the probe, if it goes beyond that, then there will be a doubt whether this is the tube or the neighboring tube is the right tube. That is one aspect. Okay. Second thing is, the entire device, when during the fabrication, can give rise to a lot of fabrication tolerance errors, because it is a precision robotic arm.
Correct.
So once the entire system, see, actually, I just would like to emphasize that point through one of the sketch, probably. Yeah, here this may be good to explain. See, actually, this is the target reference plane. And if you see here, mechanically it is coupled through the flange, and then it comes through this for the reference of the robotic system. So robotic system, though it is working very close to this, but the mechanical route is through this, which means a lot of fabrication comes into play. One is the manhole is there, flange is there, then our system, which is a ball screw mechanism. Any kind of slightest error in the system can cause a huge tilted operation of the robotic system. So that is precisely the reason we sensitized on calibration of the system after the deployment, 3 point. So instead of going for very stringent tolerancing, though we followed our stringent tolerancing, but still some of the errors are, it is not correctable, because the reason is the deployment module sends the system all the way down from top to here. So if there is some kind of flexibility coming here also, which can lead to secondary effects, which will cause some kind of bending on this slope. So this plane and this plane, never we can theoretically, in practically, we can never match them. So we wanted to observe these errors through the calibration algorithm. That is the reason the 3 point we do and do the correction based on the tilted condition. If you see here, in this tilted plane, 3 positions, what are these errors? We measure and we live with this tilted condition, but do on the fly correction. This tilted condition comes from the tolerancing and the kind of compliance in the robotic system, which would have caused the robotic system operate in a plane which is not parallel to the actual tube sheet.
Correct. Okay, thank you, Winston. Any more question, please? Audience? Audience, any more question? So, thank you, Winston.
Thank you so much.
Thank you for your good project, which is blended in the civil engineering at the time of mock-up setup you are made, and image processing subject you are added in that optical measurement, image processed, and your gear designed and gear measurement, gear rotation you are calculated by applying your BS standard and mechanical engineering, and a little bit electronics also you are added for getting the signal out of that, and communication engineering you are added for GAN bus application, and computer engineering you are applied in Python programming, IEC 6131.3 application, and PLC code you are developed, and genetic algorithm effectively you are utilized, and Kalman filter also applied. You are getting the result of the project very fine, accurately determined goal you are achieved. Thank you, Winston. Thank you for your novel project.
Thank you.